So our next speaker is Claris Castillo. She is from RENCI. We know her well. The title of her talk, I think, still, is iRODS in the Cloud, SciDAS, and the NIH Data Commons.
Can I leave this here? Good morning, everyone. I'm Claris Castillo. I'm going to be introducing two projects that use iRODS in cloud environments. The first one is an NSF project that called SciDAS. And the second one builds on SciDAS and is an NIH project called Helium Commons, which is funded by the NIH Data Commons program. So to start, SciDAS is a CC Star data project in its second year and is in partnership with Clemson and Washington State University. And this is a cyber infrastructure project. It stems from the need of scientists from the partner institutions, in this case Clemson and Washington State University, to run very large scientific workflows on really big data. And what these scientists have encountered, and the reason why we built this partnership and started this project, is that running large scientific workflows on big data is very challenging. And it's very challenging for various reasons, but the reasons I'm going to be focusing here is more from the infrastructure perspective. So this is the kind of environment that a scientist, a bioinformatician from Clemson and Washington University, or any, work with. It's very complex, it's very rich, it's very heterogeneous. If we start from the bottom, just the storage infrastructure, these scientists work with data that is hosted on storage resources across campuses. And they, in absence of iRODS, have to deal with the management of this data on their own, and that's very challenging. For computation, some of the scientists run in resources that are in the local institutions, but these scientific workflows are so large that they leverage resources that are available on shared cyber infrastructure like Seed, Open Science Grid, NSF clouds, and public clouds, which is an increasing trend that we're seeing in academia. And the challenge is that when you run these workflows, because there is no way of aggregating these resources that are across multiple infrastructure in one single pool, a scientist only have access to an allocation of resources within one infrastructure at a time. That means that if a scientist has an allocation in AWS, it can only run a workflow within AWS. If simultaneously the scientists also have access to resources in NSF Cloud or OSG, it cannot really aggregate those resources to scale. So that is a challenge. And then if you go a level up, there is a broad range of tools. I mean, the last time I checked, like, I think Wikipedia has a page that shows like all the workflow management systems that are out there. They're like 200. And just the number of tools keep increasing. Now, thanks to containerization, Docker containers, and others like Singularity, now we're able to make more easy the portability, the provisioning and packaging of these tools. So that makes things easier in terms of, from the point of view of sharing, but that doesn't mitigate the challenge that I described earlier. You can run the tool everywhere, but you still have the problem that the infrastructure is very heterogeneous. So RENCI, our team took this challenge, and our position is to leverage the advances of cloud computing, how mature this technology is, and other virtualization technologies for storage, network, and compute to create the illusion of a very big computing. So in other words, how we put all these layers that are in this ecosystem together and give the illusion of one single big computer to scientists so that they can interface with it in the same way they interface with resources in their local institutions. So break down one layer at a time. First, well, we need to abstract or virtualize the storage infrastructure. How do we do that? iRODS, right? So as I mentioned earlier, these scientists for this particular use case have data hosted in RENCI, Washington State University, and Clemson. So this particular pilot This particular use case actually drove the first implementation of the distributed metadata catalog implementation that was presented in UGM last year based on MariaDB, which I think that has migrated to Cockroach or is in the process of that. And that was pretty exciting because we were able to demonstrate that we have this iRODS deployment over the wide area network. And we work also with Internet 2, which I think is somewhere in the room, to demonstrate that the performance of transferring data over the resources was very critical and was really good. Then we want to level up, and we say, well, what is the iRODS for compute resources, right? And then we leverage a technology that called Apache Mesos to abstract compute resources across this various infrastructure. And since I only have 20 minutes, we took that open source technology and we extended so that we could deploy Mesos across multiple cyber infrastructure. We did it over public clouds and NSF cloud and Heterogeneous, and demonstrated that we could treat those compute resources as one through a single abstraction, hiding the complexity of the heterogeneity. And finally, we leverage containers for containerizing or packaging the scientific applications, but we went a level beyond, and we wrap up these containers in an artifact or an abstraction that called SciDAS that includes all the information needed to run a scientific workflow in this type of infrastructure. And finally, once we abstract everything together, it's like kind of building a big machine, we have to create sort of the operating system, the middleware that will stitch the iRODS, the data management layer, the compute management layer, the application of high-level artifacts into a cohesive infrastructure that could orchestrate the provisioning of workflows, that could optimize. We develop optimization algorithms that would place the computation close to the data, and for that we leverage all of the richness and capabilities of iRODS and other technologies that we work with. And finally, last year in supercomputing, we demonstrated that as scientists, we demonstrated two main metrics, right? We demonstrated that it was much faster to deploy a scientific workflow across multiple clouds and multiple cyber infrastructure through SciDAS than deploying it on one single infrastructure as is the state of the art without this type of technology. And we also demonstrated, of course, that scientists, by having access to, by being able to aggregate storage, data, and compute into one single machine, we're able to scale and run that execution workflows much faster than with the state of the art. Now I'm going to transition into the second project, which builds the previous one. This is the NIH Data Commons project. Helium Commons is the name of our team. This is a project, for those not familiar with NIH Data Commons, Data Commons is a program that seeks to support the development of a shared environment where scientists can come in to share data and tools that will serve as the foundation or the building blocks that will enable forward-looking capabilities that will support future science going forward. So NIH have funded 4 teams to build an infrastructure, what they call full stacks, that will enable that vision. And Helium Commons is one of the teams, is our team. The PI of this program of this project is Stan Hall from RENCI, and these are the 7 institutions with which we're partnered. And the goal is to build a stack, a full stack, that provide as a minimum the capabilities that are described, that are presented on the slide. It will allow scientists to share, 10 minutes, share data and tools, allow them to discover them. It will allow to execute workflows in a way that is sensitive to the security controls or the security requirements of the data that are typically found in the NIH community, which is often biomedical data. And it will support the provisioning of workspace environments where the scientists can interact with data and tools fluidly. It will support search and indexing. It will support a consistent, global, and unique identification of data throughout the life cycle of the data. It will embody the FAIR principle from end to end. It will provide the security controls required to support the broad range of data that will be hosted in this platform. But more importantly, well, not more importantly, but more relevant to this talk, it has to leverage the cloud infrastructure, the scalability, and all the new services that are coming out of the cloud providers in a way that abstract and hide the complexity of the heterogeneous world of cloud providers, which, as you all know, we have 3 or 4. I never know if it should include the 4. And it should do it in a fluid manner. And I think this is where iRODS comes into place. So what did we do? Well, we built on what we learned building SciDAS and took iRODS and deployed it across 3 clouds. This provides an abstraction in addition to all the capabilities that are already embodied in iRODS and that most of you are familiar with. And we have, in addition to the core capabilities that iRODS provide, adopting this technology for the data commons allowed our stack to provide 3 unique capabilities or 3 data sharing models. The first one is the default, right, that we can provide a continuous virtual system while retaining control of each endpoint when the data is hosted across the 3 clouds. The second one is what we call the bring your own data capability, which is that we leverage the plugin architecture of iRODS to develop plugins for the 3 cloud storage. So we had developed plugins there was already one for AWS. We had developed plugins for Azure and for Google Cloud, and we're able to enable seamless access of data that is hosted in the cloud through the iRODS data management layer, and this is basically the foundation of our common stack. And the third capability, which excites me the most, is what I call the bring your own data service, which is that we recognize that there are various external data services out there, and we were going to keep seeing a larger number of these data services. Like, for example, we know Globus has, 40,000 endpoints. We have Dropbox. We have Open Science Framework. And all these data services are used by scientists to host and share data. So we have created plugins. For example, we created plugins for Globus that enable seamless access to data that is hosted in Globus endpoints. And we're currently developing a plugin for Open Science Framework for Dropbox so that we can also enable seamless access to these external data services. This sort of allows us to build an ecosystem, I like to think as an operating system for data, in where you bring your own data service. And it's by virtue of that model, we enable a cost-fair sharing model, I'm done, in where as scientists, one of the challenges that NIH and other communities face on getting adoption in the cloud is that it is expensive to store data in the cloud. But if you enable these external data services, the data remains hosted outside on the external data services and is only ingested in time when a data consumer needs the data and sign a data user agreement that might be associated with the data. So that's why this particular capability, the bring your own data service, is so critical to support the data commons and foster the adoption of cloud storage for the scientific community. This is, I'm not going to go deep into, but this is the whole architecture. In the previous slide, I only focus on iRODS, but we stitch iRODS with its compute counterpart, which is DCOS, which is a production version of the open source Apache Mesos. And we have built higher level middleware services for search and indexing, partnering with scientific groups that have developed tools for ontologies and others. And thank you. Was that fast? Hopefully not.
It's a lot.
Well, it's a lot. I try to.
That's how it
Impressed.
works, right? Does anyone have any questions about this? There's a lot to take in there. There's a lot of depth. There's a lot of abstraction. The two other plugins that you talked about, they were derivative from S3, and they were basically written in under a week each to talk to Azure and to talk to Google Cloud Compute. They're already public. They're in the S3 repo. They're just sitting right there beside it. Anybody have any questions about this? Yes.
Hi. So the commercial clouds will always want to add value to their. I got it. Okay.
I cannot see you, I cannot hear you. It's just a coordination problem.
So the commercial clouds will always try to, and rightfully so, add value to their services by adding complexity, basically. And there are also capabilities that people would want. Do you envision advertising or making those noble and accessible in this commoditizing layer?
Yes. You mentioned, you were referring to cloud services, right? You said cloud services?
Yeah. So,
Yes, so
AWS and Azure are always going to add value by adding features and things like that.
in the data commons, actually, we're partnered with Google. We just yesterday, we were working with them on finding ways of integrating their search and indexing capabilities. They have a lot of really advanced search capabilities that they want to merge with some of the ontology-based solutions that are coming from our big team. This one is not from RENCI, it's from Lawrence Berkeley. And we also work very close with AWS and Google. They clearly have an interest of being able to advertise their services through our platform. Our stack, in particularly, is different from the other stack in that it's a platform. Like we are developing the billing mechanism so that we can bill users that are running on the cloud. So for the cloud provider, it's critical that we also provide endpoints or access points for those services, in particular for the genomics community, that they have very mature technology in that area.
Great. Just one quick, it's not that quick, but did you consider a singularity for its security issues, benefits?
So actually in supercomputing last year, I met with Greg, the CTO of Singularity, and we're looking at ways of extending Mesos so that it can also provision a Singularity. It's interesting that Singularity actually came out in the very early conversations of the data commons because obviously the security aspects and the security capabilities that it has. But so far, all the stacks are using Docker, but we're definitely looking into integrating Singularity in our stack.
All right, last question from John.
So there's been some high-profile cases where organizations have run out of their budget by using cloud compute and allowing people to spin up a whole load of stuff that they weren't aware that they basically ran through their entire facility budget in a fairly short period of time. How are you managing the cost management with all of that?
Great
especially
question.
with the data?
So one of the things that I didn't have time to show in the presentation is that one of the first things we did early last year was cost. I mean, there are various aspects to it. And Mesos, in combination with iRODS, allow us to support various optimization mechanisms. So first, we always place computation close to the data. We use iRODS to identify the physical location of data, and we place the computation in the same US region of the cloud to make sure that we're not incurring in egress costs. The other thing is that we use the ability to associate metadata with the resources in iRODS, and we have the same capability for compute, and we leverage the information we have about the infrastructure to combine it with billing information and minimize the costs associated with running the applications when we make the placement decision of where the applications go.
And that's all done dynamically, right?
Yes.
Yeah. Oh, all right, we got a break, but Manny's going to eat up your break. Here we go.
Should I get off? Oh, sorry.
This is the last question.
You said you have a Globus endpoint plugin. Is that plugin for iRODS or or are they different?
Can you repeat the question, please?
The Globus plugin endpoint, is it iRODS plugin where iRODS can consume Globus endpoint as a source?
The author is right in front of you. Kyle actually developed that plugin. So
Okay.
and Kyle can go way deeper than I just reached the globus, and that's the end of it. So, so we have an iRODS, we develop an iRODS plugin so that we can provide access to data hosted in globus endpoints. So it is an iRODS plugin.
Yeah, the last one is regarding the metadata. So you said you are exposing the GCP and Azure and AWS as a storage virtualized through iRODS. Is it scientists can push the metadata, user-defined metadata through iRODS and also read it back if someone is adding outside of the iRODS directly in AWS? Is it plugin supports right now, or it's a custom built on top of it?
That logic is not encoded in the plugin,
Right.
but it's basically how the ingestion pipeline works, right? So the data, we ingest the metadata into iRODS, we keep the data in the resource, either the cloud storage or in the case of Globus, outside the cloud perimeter on the Globus endpoint, and that way the data is findable. But when it's findable because we index the metadata, but when a data consumer wants to access that data, this is the fun part, right? The user has to agree to ingest the data into the cloud environment and pay for storing that data for processing.
Excellent. I think that's it. All right. Thank you so much.